Hi, everybody. In this portion of the video, we are going to be walking through a von Neumann stability analysis, which is going to demonstrate why our model that we made in Python becomes unstable at R values of greater than greater than 1/2. So the first step in constructing, the first step in constructing this stability analysis is beginning with the heat diffusion equation that we began with to construct our finite differencing model for the heat diffusion problem. So go ahead and write that on the board. So in the previous video of constructing that finite differencing model, we recognized that there were a few assumptions that we could make about our heat diffusion equation in the Cartesian coordinate system in order to simplify it down. That was that there was no heat generation and that we were only concerned in the x direction. So I will go ahead and, I will go ahead and write out that heat diffusion equation with those assumptions in mind. So the way that heat diffusion equation looks with those assumptions is the partial derivative of temperature with respect to time is equal to alpha times the second derivative of temperature with respect to position. So again, symbolically, we have d temperature over d time is equal to alpha times the second derivative of time. So differential squared of temperature, not time, temperature, over the second derivative of position over dx squared. So from here, we're going to identify a potential solution for our heat diffusion equation. And that potential solution, I'll put a box around it so that we can see it, is going to take the form of temperature is equal to e to the power of I k x, or I is the imaginary number, square root of -1. K is, our thermal conduction coefficient, and then x is our position x. So it's going to be e to the ikx times e to the negative alpha times k squared times t, which is going to be time. So I'll put a box around this. We're going to walk through a brief proof or a brief demonstration that this is in fact a valid solution to our heat diffusion equation. So if we plug in this expression for temperature into our heat diffusion equation, we'll get something like this. So we've got partial ddt time of e to the ikx times e to the negative alpha k squared t is equal to alpha times, second derivative with respect to position of that same value for t, e to the ikx times e to the alpha k squared t. Now, if we walk through these derivatives, we will find that this is, in fact, a true statement showing that this expression for temperature is, in fact, a valid solution. So we take the first derivative of this temperature expression with respect to the first derivative, which is with respect to time. Because of the way log rules, the natural log rules work with derivatives, you'll have to pull out the coefficient of t here, which is going to be negative alpha times k squared, and then just rewrite this whole expression since it just consists of powers of e, so e to the ikx, e to the negative alpha, k squared t equals, keeping alpha outside of our derivative, and we're taking the second derivative with respect to x. So it's going to look like the same process, but it is just going to be the coefficient inside the power of e of x. So it's going to be ik. So we'll pull that out. We're going to pull it out twice because we're taking a second derivative with respect to x. So we're going to have alpha times I squared times k squared, again, because ik is coming out twice, and then times that whole expression once more, e to the ikx times e to the negative alpha k squared t. So again, this is our expression once we have plugged this into our heat diffusion equation. Now these look like different things, but in fact it is the same because I squared, again, I is the imaginary number that is the square root of -1. So I squared then becomes -1. So we have negative a and then negative a, and then the rest of this k squared times that expression t, k squared times that expression t. This is then a true statement, which demonstrates that the expression for t inside of the box is in fact a valid solution for our heat diffusion equation. So I'll go ahead and just write a true statement here. Underline that. I'm going to write a big check mark next to this box, again, because we have demonstrated that this is a valid solution for our heat diffusion equation. So the next step is going to be relating this expression for t back into our finite differencing way of expressing the heat diffusion equation. So it's going to be T in terms of T sub j, which is our position vector, and then superscript n, which is our not position vector, position index, and then superscript n, which is our time index. So I will go ahead and write that out. So instead of just T, we're going to have T sub j superscript n is equal to E I K. And then instead of just X, we're going to have N delta X because we are incorporating that index. We're also going to have E to the negative alpha K squared. And then similarly, instead of T, we're going to have, we're going to have N delta T in the second power of E. In the beginning, that's going to be J delta X, not N delta X. Not to worry. So again, to repeat, when we're incorporating our T, J, N expression of T, it's going to be T sub j to the n is equal to E to the ik j delta x, and then E to the negative alpha k squared, n delta t. And again, that's just incorporating our j and n indices or indices for position and time, respectively. So the next step for this stability analysis is going to be recalling our heat diffusion equation in terms of finite differencing. So I'll go ahead and write that out as well and narrate as I do so. So the way that that expression looks, or that equation, so we get T sub j to the n plus 1 is equal to T sub j to the n plus r, and then r is multiplied by the quantity Tj plus 1 to the n minus 2 T sub j to the n plus T sub j minus 1 to the n, close bracket. So again, this is the expression of our heat diffusion equation in terms of finite differencing. And this is the model that we use in our co-laboratory demonstration of our heat diffusion problem. Again, which as we will see here, we observed an upper limit of 0.5 of R. And at that point, it's the maximum that our model remains stable at. And at any values of R higher than 0.5, 1/2, our model goes nuts. So again, this stability analysis will demonstrate why that is the case. So from here, we're going to plug in, we're going to plug in this solution for our temperature into our finite differencing model of our heat diffusion equation. And when we do that, we're going to keep Tjn, T sub j to the n, as a factor. And then whenever there's a modification of our position index j, we're going to express that in terms of E from this expression of T. So I'll go ahead and carry that out right now. So we have Tj to the n plus 1 on the left. That's going to remain the same. Is equal to, again, we're factoring out Tjn, so we're going to keep that the same. Actually, we'll do one step in between. So we're going to keep that Tjn plus r, and we'll open that same bracket. So in this case, we have T sub j plus 1 to the n. So again, instead of having just j in our formula for Tjn, we're going to have j plus 1. So all of that's going to be the same, and then we're going to have an additional factor of E to the ik delta x. So I will instead write, instead of T sub j plus 1 to the n, I'm going to keep that as T sub j to the n, and then just multiply that by that additional factor, because we have j plus 1, of E to the ik delta x. Minus 2 Tj to the n, that's going to remain just the same as it is before. And then lastly, we're going to have plus Tj minus 1 to the n. Now, again, we're going to keep this as Tj. And then because we're plugging in j minus 1, similarly, we're going to get that same factor, which is going to be this an additional factor, added on or multiplied to this expression for Tjn. That additional factor is going to be E to the negative k ik delta x. So I'm going to add that in as well. E to the negative ik delta x. Close that parentheses, close that bracket. So again, once we apply the solution for T to our finite differencing expression of our heat diffusion equation, this is what this is going to look like, just like that. Looks like there's an announcement in the library. Just a second. Okay, the desk is closing in just a few minutes, but that's okay. We've got plenty of time. So again, after we plug in this expression for T in terms of a few powers of E, this is what our heat diffusion equation for finite differencing is going to look like. So we will carry this up here just to give us a little bit more space. And we're going to simplify this by factoring out T sub j to the n. So I'll go ahead and do that. So on the left, keeping this the same as we have, T sub j to the n plus 1 equal to t sub j n, and we're going to factor this out in every case. So we're going to open some big brackets. We're going to do a 1 plus r and open some parentheses, and we're just going to have that additional factor because we dealt with t sub j plus 1 of e to the I k delta x minus 2, because we just have that 2 tj to the n, plus e to the negative I k delta x. Those are our additional powers of e in that equation. So from here, we're going to be able to further simplify this using something called Euler's formula. So I'll go ahead and write those out. So Euler's formulas state that if we have an expression that is e to the I x, that's going to be equal to cosine of x plus I times sine x. Likewise, if we have e to the negative I x, that's going to be cosine x minus I sine x. And these, again, are just some definitions known as Euler's formula. So if we apply these to this expression, the finite differencing heat diffusion equation with the powers of E for T, you'll notice that we can combine, we can combine these two powers of E, because we have E to the IX plus E to the negative IX. So in this case, we're basically just going to plug this in, and we're going to add these two together, except instead of just an X, we have a K delta X. So in our final equation, instead of being cosine X, we're going to have K delta X instead of just that cosine X. So once we do that, let's do some more simplification. Write this out one more time. 1 plus r times, so if we add these together, we're going to get cosine x plus I sine x plus cosine x minus I sine x. So these plus I sine x and minus I sine x, these are going to cancel, or instead of x, k delta x. So we're just going to be left with 2 cosine of k delta x. So we'll do that, 2 cosine k delta x minus 2. Close parentheses and close the bracket. Now, just for the sake of simplification, we're going to take this 2 out, place that with a 1, take that 2 out, place that with a 1 that's assumed. We're going to take this 2 outside, right over here next to the r. Again, just rearranging some coefficients. Now, from here, this is the farthest we're going to get in terms of simplification, but to, again, demonstrate why that limitation, the upper limit of 0.5 is placed on r for our finite differencing model, we're going to have to look at some inequalities. There's some ranges of possible values for these factors in our heat diffusion equation. So the first that we're going to be able to point out is this expression over here on the right inside these brackets is going to need to be between -1 and +1. Now, if you note, I'm going to use y just as an arbitrary variable to represent anything that I underline or put a bracket or a brace around, just to make these inequalities a little bit easier to read. Y has no bearing on our actual equation. That's, again, just an arbitrary variable to represent whatever I'm circling here to talk about these inequalities. So this expression here, everything inside the brackets, needs to be between -1 and 1, because if it is outside of those ranges, any temperature at any position T sub j to the n times something greater than 1 or less than -1 is going to be equal to the temperature at some unit of time later. So T sub j to the n plus 1. Again, we're going from n to n plus 1 at a specific point in space, a specific point in our system. So again, if this factor is greater than 1 or less than -1, every time we index that time, every time we add 1 to n and move forward in time, we're going to be increasing T sub j to the n, that temperature, that specific point in time and point in space. We're going to be increasing that steadily every time that we go. Grab some water. So at lower values, this might not seem like too big of an issue, but if we allow our time to approach infinity, that means our temperature is also going to approach infinity, which from a physical perspective doesn't make any sense. So that's why we have that limit on this expression here. So again, this has to be between -1 and 1. So we've got our 1 plus this quantity here. So let's just take that out. So next we can simplify this down and say 2r times cosine of k delta x minus 1, close parentheses. This is going to have to be between -2 and 0, because we're just taking these same bounds that we placed above and subtracting a 1. So -1 minus 1 is -2. 1 minus 1 is, of course, 0. So these are the bounds here. Now, if we zoom in a little bit into this expression, we're going to see a cosine function. So we know that the cosine function is bounded similarly between -1 and 1. So we'll go ahead and circle that too. However, we've got a -1 here as well. So take a slightly bigger brace and represent this whole factor, everything but 2r. We're going to notice that this also is between -2. Yes, yeah, oh, good, yeah, because we are going to subtract that 1. We're going to have -2 and 0, just like we did before. And if we take this 2 off of here as well, looks like I skipped a step. I'm gonna back up a few steps. I don't want to record a whole other video, so I'm gonna back up just a few steps. Let's see. So we're back here. We know that this whole factor has to be between -1 and 1. So if we subtract that 1, we're gonna get this right here between -2 and 0. So if we take this 2 off, we're just gonna have r times cosine k delta x minus 1, taking the exact same thing and just dividing by 2. We're going to take that limit, inequality, down to -1 and 0. Now from here, we're going to repeat those same steps as we did before. Our cosine function, cosine of anything is limited by -1 and 1. If you subtract 1, that whole thing with that -1 is going to be -2 and 0. Now from here, everything within the parentheses we know is going to be bounded between -2 and 0. If we include r, we know that this entire expression is going to need to be between -1 and 0 for this physical expression of our heat diffusion equation to make sense physically in real life. So our r coefficient is going to get us from this bound to this bound. So if we know that this entire thing has to be between -2 and 0, if we add r, it has to be between -1 and 0. From this, we can reason that r must be between, rewrite that, r must be between 0 and 0.5. And this concludes our von Neumann stability analysis. This just demonstrates that mathematically and physically for this model to make any sense, r has to be less, let's see, r has to be less than 0.5. Otherwise, we are infinitely increasing our temperature, which doesn't really make any sense. And in the collaboratory model that we constructed, if r is greater than 0.5, and we tested the value of r equals 0.55, we actually saw this temperature increasing to infinity. We were getting ridiculously high orders of magnitude of our temperature. So again, this concludes the von Neumann stability analysis, demonstrating that r must be less than 0.5 in our finite differencing model. Thank you.